I am working through coupled oscillations and normal modes, and one of the examples that often comes up is the double pendulum. And let's just be clear, the double pendulum is a really complicated system. It's really difficult to model because the motion of this, even though there's only 2 degrees of freedom, the motion of this one depends on the motion of that one, and it just gets really messy. I did do it. I derived the equations of motion for a double pendulum using Lagrangian mechanics, and I will post the link to that down below. But in this case, what we want to do is to find the normal modes. So remember, normal modes are the situations where the motions of the 2 variables, theta 1 and theta 2, or some other variables, we're going to use some other ones, have the same frequency. So it's initial conditions that give those same frequencies. And I'll show you what I mean when I get there. But now we're going to use a special case. I'm going to write it. Special case. Theta is small. So very small angles, and it's such a small angle that we're going to make some really crazy seeming approximations, but at the end it will indeed work. For a normal pendulum we make approximations too. You hear, oh, theta less than 15 degrees, and that allows us to get a simple harmonic motion for a pendulum. It's similar to that, but it's a little more extreme, and I don't really like it, but it does make it work. Okay, so I want to represent the motion of these two with the 2 coordinates x1 and x2. So I'm going to call this x1, and I'm going to call this x2. And I drew these angles big, but they're actually very small. And they're so small that there's no vertical motion. Which is crazy, right? Because if you have a pendulum swinging, even at the bottom, it's moving in a circle, so it is accelerating up because it has circular motion. But we're saying no, it's not. No, it's not. It's not even doing that. Okay, so let's go ahead and write down x1 and x2 in terms of theta 1 and theta 2. Again, if theta is very small, then I can say x1 is equal to r times theta 1, right? Because it's just the arc length of this, and that's r theta 1. Now x2 is going to be equal to x1 plus this length plus r theta 2. And I'm using a special case, same mass, same lengths, just to make things easier. So x2 is going to be r theta 1 plus theta 2, right? Because if I put in theta 1 right there and factor out the r, I get that. Next, I want to write equations of motion for both of these masses. So I'm going to draw a free body diagram for this one that's going to be weird, very weird, and this one too. So this one I'm going to have, here's my mass. I have gravity pulling down. I'll call that mg. And then I have this string pulling up. So that's going to be, I'm going to call that T1. I'm going to draw it not the same angle as that. I'm going to draw it like this, T1, and this angle is theta 1. And then I have T2 pulling this way. Draw it a little bit bigger. T2, and then this angle is theta 2. That's the same as that. And then for this mass over here, it's a little bit easier. I just have T2 pulling this way. T2, and then this angle's theta 2, and then I have mg. So let's write down, I've already said, write down the y equation of motion. I've already said that they don't move in the y direction, so they don't accelerate in the y direction. If they don't accelerate in the y direction, the net force in the y direction has to be 0. So technically this one would be 0, the net force is 0. It would be T1 cosine theta 1 minus mg minus T2 cosine theta 2. But if theta is very, very small for both these cases, then this is approximately equal to 1. So I get 0 equals T1 minus mg minus T2. And so that would be the same case if this was hanging vertically. You could easily see that, right? It's not vertical, was kind of. And then for the other one, I'm going to get T2 cosine theta, so it should be 0 equals T2 cosine theta 2 minus mg. And again, I'm going to just say that's 0, so I get 0 equals T2 minus mg, or T2 equals mg. And then once I know T2 is mg, then up here, I could say T1 is equal to 2 mg. Is that okay? So again, if you had the simple case, which is almost what we're going to have, this, then you could see that this string tension would be twice the mass, and this would just be single mass. Okay? I know it doesn't seem great. Now let's go to the x motion. So I want to use these same diagrams, so I'm just going to put this right here. So let's say x motion. And let's look at this one. So I'm going to say mx1 double dot. That's the acceleration of mass 1 in the x direction. Well, what forces are in the x direction? Well, I have a component of T1, right? I have a component of T1. I'm just going to write that as equal to negative T1 sine theta 1, right? Because that's the adjacent side. That's the adjacent component, the opposite component of this, pulling in the negative x direction. And I know where he said, well, it's already vertical. You can't do that. Well, I'm going to do it. And there's nothing you can do. You could stop the video if you want. You can say, I'm not going to watch this. And I fully respect your decisions as a human. You do what you think you need to do. The gravity pulls in just the y direction, and then I have this in the x direction, which is going to be plus T2 sine theta 2. Let's do the same thing for mass 2. mx2 double dot. This one only has one force in the x direction. It's going to be negative T2 sine theta 2. Okay. So now we have x's and thetas, and I only want x's. I'm going to get everything in terms of x's. So if we go back from before, from our definition, I've wrote it up here. We could also say sine of theta 1, just looking at this diagram, sine of theta 1 is going to be x1 over r. Sine of theta 2 is going to be equal to this distance right here over r. And this distance is the total distance x2 minus x1. So this is going to be equal to x2 minus x1 over r. And so you could say, oh, I'm going to let sine theta equal theta, but it doesn't really matter. I've already done this. I'm going to get rid of the thetas, and so I'll just have equations in terms of x. So let's put these in. I get m x1 double dot equals negative, and I'm also going to put in T1 is equal to 2 mg, T2 equals mg. So if I put that in, I get negative 2 mg. Sine theta 1 is x1 over r, plus mg times sine theta 2, which is x2 minus x1 over r. Now let's do the other let's do the other one. mx2 double dot. Let me just say, it is very possible to write everything in terms of theta 1 and theta 2, theta 1 and theta 2 dots, double dots. That is possible, okay? But if you do that, you end up with a little slightly different version of this equation for the eigenvalue problem, and maybe I'll do that later. But I kind of like it this way better, because it looks like the stuff that we've done before with masses on springs. But I digress. Okay, so here we are. I have negative T2, which is mg. Sine theta 2 is x2 minus x1 over r. Okay, now what I want to do is to get this in the form of something times x, something times x1, something times x2. So the first thing, I can just cancel all the masses. The masses all cancel, right? We're cool with that. So let's go down here and rewrite this equation. x1 double dot is going to be equal to negative 2g over r x1, and then I get plus g over r x2 minus g over r x1. And I want to gather the x1s together. So I'm going to write this as negative 2g over r plus g over r, because I factored out the negative sign, x1, and then I have plus g over r x2. And that's x1 double dot. Now let's do the same thing for the other. x2 double dot is just going to be equal to the mass canceled. So I get, I'm going to do the x1 first. I have negative g over r times negative x1. So this is going to be g over r x1. And then I have minus g over r x2. I'm just checking. Okay. That's my other equation. So now let's write these down. This I can simplify, right? Because that's just going to be 3g over r. So let's write these down. Just rewrite them. I'm going to write it right here. So x1 double dot is equal to, I'm going to factor out the g over r. So I have g over r times negative 3x1 plus x2. And then this one, x2 double dot is equal to g over r times x1 minus x2. We are ready to rock and roll. This is a nice equation right there, okay? Because now what I want to do is to assume a normal mode. If I assume a normal mode so that x1 and x2 have the same frequency, then I can write, and this is the same thing we did for the other eigenvalue problem. So if you want a more detailed review of that, I'll put a link down below. So I'm going to say, I'm going to define the solution as a vector x equal to some vector a1, a2 times e to the minus I omega t. So that x1 will be a1 times that, x2 will be a2 times that, but they have the same frequency. And yeah, that's an imaginary complex number, and we're going to take the real part of that, but it doesn't really matter. Now, if I take the derivative of this twice, because I need to write these as a vector, I can say x double dot. I'm just going to take the derivative of this twice, I get a negative omega squared a1, a2, e to the minus I omega t. And so now you can see I can rewrite this equation as the following. I can write this as x double dot equals, and I'll pull that g over r out front, g over r times negative 3, 1, 1, negative 1, x. And if I take the derivative, I can replace this with x, and I actually get, I'll write it out the full way, negative omega squared x. No, let's write it out. a1, a2, e to the minus I omega t, right? That's just that right there, equals g over r, 3, negative 3, 1, 1, negative 1, a1, a2, e to the minus I omega t. And some magic stuff happens here. In particular, I can cancel these two terms. Yay. I'm going to multiply both sides by a negative just so it looks like the way we like it. So I'm going to say omega squared a1, a2 equals, let's put this as just g over r. I'm going to bring the negative sign in there. 3 minus 1 minus 1, 1, a1, a2. And so now we have, this is the eigenvalue problem. Because this says, I want to find some vector, a1, a2. These are just constants, where I operate this matrix on that vector, and I get the same vector back with the scalar multiplied by it, omega squared. And that is the eigenvalue problem. So we can solve this by multiplying this by the identity matrix and subtracting it from that side. And what happens is you get this characteristic matrix that is only gives you only gives you solutions if the determinant's 0. And I'm skipping over a lot of stuff there. But so let's write this equation right there. Omega squared A1 A2 equals G over R 3 minus 1 minus 1 1 A1 A2. Okay, so this will only give, so then I can subtract this vector from both sides after multiplied by the identity matrix, and you actually get 0, 0 equals G over R 3 minus omega squared minus 1 minus 1 1 minus omega squared A1 A2. And this will only be non-zero, only give solutions if the determinant of this is 0. So we're going to take the determinant of 3 minus omega squared minus 1 minus 1 1 minus omega squared and set that equal to 0. And by doing that, we can solve for the values of omega that work for here. Those would be our eigenvalues. Okay, so we can take this determinant. So it's going to be this times this. So 3 minus omega squared times 1 minus omega squared. And then this times this is 1. So I get minus 1 because it's this times this minus this times this. This times this is negative 1 times negative 1. It's 1, but I get a minus. And then I get 0. I set it equal to 0. Now let's just multiply this out. I get 3 times 1 is 3. 3 times negative omega squared is negative 3 omega squared. And then negative omega squared times 1 is negative omega squared. Negative omega squared times negative omega squared is plus omega to the 4th. And then I have a minus 1 equals 0. So let's just combine our terms together. I get omega to the 4th. And then I have negative 3 omega squared. Do I have the right? I think this is the right equation. I'm just going to double check. So I have negative 3 omega squared minus 1 omega squared is going to be minus 4 omega squared. And then I have plus 2. I feel like that's wrong. I'm just checking my work. Because, you don't want to just work through a problem and not know what you're doing. You want to at least check your work. Okay, that's right. Yeah, I think it's right. Okay, so let's now write that equation because we want to solve that equation. What values of omega solves that equation? So I have omega to the 4th. I already forgot it. Minus 4 omega squared plus 2 equals 0. So if I can solve for omega squared, right? Because this is, I'll rewrite it, omega squared minus 4 omega squared plus 2. And so now it's a quadratic equation for omega squared. And so remember, if I have a x squared plus bx plus c equals 0, then x is going to be negative b plus or minus the square root of b squared minus 4ac over 2a. So let's do that for this. So omega squared is going to be negative b. So negative b is 4, right? Because b is negative 4. So I get 4 plus or minus the square root of b squared, so it's 16, minus 4 times a is 1, c is 2. So 4 times 2 is 8. So minus 8. All that over 2 times a, which is just 2. Okay, so I get omega squared is 4 plus or minus the square root of 8, which is going to be 2 times 4. over 2. So it's going to be 4 plus or minus the square root of 2 times the square root of 2 divided by 2. So this is going to give me 2 plus or minus the square root of 2. So I get omega 1 is 2 plus the square root of 2. Omega 2 is 2 minus the square root of 2. So those are my two frequencies for x, not for theta. Okay, for x. But what I want to do is to find the values of A1 and A2 that will make this normal mode. Those are my initial conditions. So how do I find A1 and A2? Well, I got to go back to the original equation. So let's go back to this. Remember, we have this. Omega squared times A1, A2 equals G over R times the vector. What was my vector? My matrix. It was 3, -1, 3, -1, -1, 1 times A1, A2. So I want to put in my values for omega squared. Remember, omega squared equals omega 1 squared is 2 plus the square root of 2. Omega 2 squared is 2 minus the square root of 2. So let's use omega 1 squared. Oh, you know what? That's wrong. G over R. G over R. Why did I not do that back here? Let's go back. See, I had that G over R there. So when I take the determinant of that, that G over R should be in these terms too. So there's a G over R that I dropped out, which is good, right? Because G over R is the frequency that does give units for frequency. So sorry for that, but I think we're cool. Okay. So if I put that in, with the G over R is going to cancel, which is kind of nice. So let's put in omega 1 squared. So I get 2 plus the square root of 2, A1, A2 equals 3, -1, -1, 1, A1, A2. So let's just do this first. This is actually two equations, right? This times A1 is this times that. So I get 2 plus the square root of 2, A1 equals 3A1 minus A2. Because I do this, that. Now let's just get, I'm going to move this to the other side. Let's get the A1s on one side and the A2s on the other side. So I get 3A1 minus 2A1 minus the square root of 2A1 equals A2. Yeah, because I moved this over there. I added A2 to both sides and subtracted that, just so it makes it look nice. And then I can factor out the A1. I don't know why I did that the other way. So I get A1 times 3 minus 2 minus the square root of 2 equals A2. And so this is going to be, actually, let's do this as plus or minus, plus or minus. Actually, it's minus or plus. Minus or plus. So I get A1 times 1 minus the square root of 2 equals A2. Or, this other, if I put in omega 2, I get A1 times 1 plus the square root of 2 equals A2. So these are my eigenvectors, because now I can say, let's say if A1 equals 1, then I get the vector, the initial conditions vector of 1, and then A2 would be 1 minus the square root of 2. And then the other one, so this is omega 1. And the other one would be 1 plus the square root of 2. And that's omega 2. Okay, so this is my initial conditions for x1, x2, x1, x2. Not theta 1, theta 2. Okay. So what if I do want to find theta 1 and theta 2, because I'm going to do that. Now I just need to go back over here, way back, oh, right there. So actually, let's just draw a picture. So theta 1 is equal to x1 over r. So and theta 2 is equal to x2 minus x1 over r. So if x1 is equal to 1, then I'm actually going to get the theta 1 and theta 2 vectors are going to be 1. I'm going to subtract this from theta 2 from theta 1, so this is going to be 1 minus this, so I get square root of 2, and the other one would be 1 minus the square root of 2. So those are my angle vectors, and these are my x vectors. Okay, let's go ahead and plot this, and then I do have an actual real double pendulum model with fully calculated, which I made before, that I'll use with these initial conditions. But I want to use these first. So what we're going to do is I have equations of motion for x1 and x2 going back. x1 double dot, x2 double dot, so I can make a numerical calculation. Now I do need to pick values for g and r, I know g, and the mass, but the mass doesn't matter. So let's use a radius of 0.1, 10 centimeter lengths, and then I'll put in initial conditions and see if it's a normal mode. I'm not going to model it 3D, I'm just going to plot it. Okay, so let's go. I am going to need these two equations right here. x1 double dot and theta 1, x2 double dot, which are right there. Okay, so let's model those. Switching over to Python, activate now. Here I am in Web v Python, and I didn't go over my normal introduction to numerical calculations. I don't know why, but g equals 9.8. Let's just get started. And then I said r is equal to 0.1. I do need to make some graphs, so let's put that in here. g1 equals graph, x title equals t, and then y title is x. And then let's put a width 500, height 250. And then I need two things to plot. f1 equals g curve. Is this big enough? That's better. G curve, color equals color dot blue. And then f2 equals g curve, color equals color dot red. Now I'm gonna in this numerical model, I'm going to make a full numerical model. So I need the initial value for x1, the initial value for x2, the initial value for x1 dot, and the initial value for x2 dot. So x1 equals, oh, and I did say what they should be. So 1. So I don't want it to be 1. x1, let's say x1 is 0.01. x2 is x1. Let's just say 1 minus the square root of 2. So it's 1 minus the square root of 2 times 0.01. But I'm going to release them from rest. x1 dot equals 0, x2 dot equals 0, t equals 0, dt equals 0.01. I'm not sure if that's big enough. Okay, while t less than 5. Let's make this run in real time. Rate 100. So the number one thing, step number 1, to calculate x1 double dot. x1 dd dot equals, now I'm looking at my paper right here with that equation, right? That's my model. And this is just for small angles. It just works for small angles. So it's going to be -3 times x1 plus x2. Oh, and all of that was multiplied by g, let's put it as g over r times, that's the way I wrote it. And then let's calculate x2 double dot, and that's going to be equal to g over r times x1 minus x, not equals, minus x2. Now that I have x1 and x2 double dot, I can calculate x1 dot, x2 dot. So x1 dot equals x1 dot plus x1 double dot times dt x2 dot equals, I normally work these out beforehand and I didn't. So if this works, I'll be very happy. Now that I have x1 dot, x2 dot, I can update x1 and x2. So x1 equals x1 plus x1 dot times dt. x2 equals x2. Oh, you can't even see that. Look at that. x2 plus x2 dot times dt. Update time. Plot. f1 dot plot t x1. f2 dot plot t x2. Seriously, if this works, you're going to have to give me a double high five. I'll give myself a double high five. My things can't see my face. And I like to see myself because, you know, it's me. Let's just run it. And this should be a normal mode. I think that's a double high five. 1, 2. I can't believe it worked. So, but you see here that these two are out of phase, right? But they have the same frequency. They both have, you know, trig function solutions, which is what we'd expect. Now, the other solution I already said was this plus that. Another double high five right there. They don't have the same amplitude. They don't have to have the same amplitude. That's pretty awesome. That's pretty awesome. I didn't even save it. Look at that. I am going to save this. Let's see. X version of double pendulum. Of course, for small oscillations, you know, you can use these normal modes to make linear combinations of any other solutions. You just got to find the initial conditions. But I just wanted to find the normal modes. But I want to see the normal modes with my eyes. Okay. So here is a double pendulum that I made before. This is the real calculation. Okay. And I'll give you the code to this. Notice down here, theta 2 double dot, theta 1 double dot, they get a little messy. And actually, because I have these A, B, C, F, K stuff in there. So it's kind of whack. But it's legit. And over here I have the same G masses, R1, R2. And here I'm starting theta 1 at 5 degrees. Theta 2 is at 0. So if you run that, it's not a normal mode, right? You can see not normal mode, not constant frequency, not the same frequency. It's still so cool. Okay, so let's put in our first normal mode where theta 2 is equal to negative the square root of 2 times theta 1, right? So that's what we said. We're switching from x's to thetas. And let's run this. And is that a normal mode? It is indeed a normal. Look at the frequencies. That's kind of cool. And this is in 3D. You can rotate it around. I'm not sure why you would, though. But there you go. It works. Next is the other normal mode is just plus. And I run that one. Again. And see, you'll notice here that they're swinging with the same frequency, but they don't start with the same amplitude, right? That's what you got to do in order to make this one have the same frequency as that one. Okay, now one last point. I made the assumption that the masses were the same, that the lengths were the same. R1 was the same as R2, and M1 was the same as M2. If that's not the case, then it's more complicated. But I think you can still do it. I think you can still find normal modes. The eigenvalue problem just might be a little more complicated. I should probably do that, just a generic one, but I didn't, and I don't know that I will because I'm running out of time here. Okay, so code down below. Other coupled oscillation stuff down below. The end. That was kind of fun, though.